Hi everyone, welcome to the first of two Restoring Refunction sessions. We're gonna go ahead and get started. I am Lauren Toth, I work at the USGS and I will be your first moderator for this session. Excited to see all of these talks about the broader impacts of coral restoration. And we are starting with Isabel Nunez.
Hello everyone. My name is Isabel Nunez. I would like to thank you all for being here. It's a great honor to be surrounded by so many coral experts and restoration practitioners. I am currently a PhD student finalizing my PhD at UTS, based in Sydney, Australia, under the supervision of David Saget and Emma Camp. First of all, I would like to acknowledge the traditional custodians of the sea and land where our research took place and pay my respect to their elders, past, present, and emerging. And so, I would like to introduce you a little bit about the current evaluation of coral reef restoration. As you know, the main metrics that we use are survival and growth rates. And the reason for this is because they are easy to collect. And they are useful metrics as well. They can inform growth rate is related to coral cover, and survival rates are also related to effective population size. So they are important metrics, of course. However, these two traits they don't provide enough information about the coral performance or health and the reef functioning during restoration efforts, during propagation and outplanting activities. And these two metrics might not capture trade-offs during these efforts as well. And as you can see in the figure, there is a biological machinery that is underpinning these three emergent properties: growth, reproduction, and survival. And therefore, there might be other traits that we could consider when evaluating the success of restoration efforts. And as well, there is an urgent need to bring other traits that are more aligned to ecosystem services, because when we do restoration, our ultimate goal is to restore this reef functioning. And this is why we decide to apply a multi-trait approach in order to deep insight into this biological machinery and try to understand how corals are performing, in this case, under a nursery propagation phase. So the aim of our project was to apply this multi-trait approach to evaluate the success of coral propagation on the Great Barrier Reef. And as you can see here, we monitor wild colonies for 1 year and their nursery fragments as well. And a little bit of the experimental design. The study was performed on the Northern Great Barrier Reef in Opal Reef. We selected this table coral, Acropora hyacinthus. We identified and tagged 6 wild colonies. And we prepared their nursery fragments. And there were 2 time points in a period of 1 year. And so we studied 93 traits. I'm going to show you fast here. All right, so with these 93 traits were divided in 7 biological sections or properties, and between brackets you can see the amount of traits per section. And briefly, for the physical appearance, we were doing divings and taking pictures with a ruler and with color cards. Then for the elementum or chemical elementals, we use ICP-MS. For energy reserve, freeze drying and different protocols for proteins, carbs, and lipids. Skeletal properties through a methodology that implies the Archimedes principle. Photobiology, our team is very has expertise on that, so we look at 13 properties related to this. Also metabolism, we did in situ experiments measuring respiration, calcification, and photosynthesis. And we also look at the fatty acids through gas chromatography. And here is some of them. I couldn't put all of them, so as you can see, for you to to see how they look like. And these 93 traits were selected based on a extensive review where I had to look in studies of coral biology, coral ecology, coral restoration, and we choose these traits based on feasibility, based on return of knowledge, how much we are going to invest and how much we are going to get in terms of knowledge, the expertise of and resources of the team, and also we had time constraints as well that we have to consider in 1 year experiment plus all the analysis. And this was me many times. Selecting them, but especially at the end with the results to trying to understand when a trait change, what does it mean for the other, or they are related. So yeah, it was a big exercise to match them, to understand them all together. And so again, for the method, as I say, 7 biological properties, and this is how I analyze the data. I first did student tests for survival and growth rates. Then for each section, I look at each individual trait through ANOVAs or Kruskal-Wallis and their post-hoc test. And then for each section, I identify the 2 main drivers through contribution plots and through variable and b-plots PCAs. And with all of that, I built a final PCA with the 14 main drivers for separation between the coral groups. And so the results, regarding survival and growth rates, here you have an example of one of our nursery fragments that grow more than 6 times in a 1 year period on the nursery. And so these are the results. Survivals rates were high, as we expected, also higher growth for nursery corals as well. And all of this we already know is expected results when you're working under a nursery, optimal nursery environment. But I would like you to come with me and discover what is leading this increase in coral growth, and also what we can gain when we apply this multi-trait approach, when we integrate these multiple traits, in order to evaluate, as I said, the success or coral performance, risk functioning of these corals during propagation activities. And so when I choose some of them, of course, I couldn't put all 93, but regarding energy reserves, for looking at total energy reserve or ice-free dry biomass, I will focus only on the environment effect, the nursery to go faster. So we didn't see any environmental effects. So this means that there was no impact on the energy reserve nor the ice-free dry biomass during the coral propagation phase. And in addition to that, we also didn't see an impact of the nursery environment on all these 6 traits. What does it mean this related to ecosystem services? Well, we are keeping the bioenergetic value to the trophic transfer when we are doing this activity, which is a good thing, right? Metabolism. So we look at, for example, light calcification and the ratio of gross photosynthesis and respiration. Again, there was not an environmental effect, not nurturing effect, meaning that at time 12, both the wild colonies and the nursery fragments, they have similar light calcification and PR ratios. However, as you can see here, we have a lower PR, which this means that in this case, it was driven by higher respiration rates of the nursery corals. And we believe that it's potentially due to an enhanced feeding on the nursery environment. Photobiology. Here we look at symbiont cell density and light saturation coefficient. There was not an environmental effect, so there is no impact of the nursery propagation on these 2 traits. However, these results are interesting because you usually will expect lower symbiont cell density and lower light saturation coefficient when you are working with shallow corals, when you are working in a nursery environment where you have high light intensities. And so this was very strange, right? But luckily, because we applied this multi-trait approach, we also look at the ITS2, okay, of the symbiont type, and we could see, maybe it's very hard right now to see, but I can tell you what we see is that this is the white colonies at time 0, and this is the endpoint. We see there was a switch the ITs2 moved to, well, they were calopodium predominantly, but they moved to the C3K radiation. And there has been studies showing that this type has been observed in genotypes that perform better under suboptimal conditions. What else? Elementum, one of them, for example, potassium. Again, there is no environmental effect, no nursery effect on this trait, this chemical element. In addition, there is not a nursery effect on all the 23 chemical elements. What does it mean? Again, we are maintaining this biochemical cycling, this important reef function. Skeletal, two other traits, pore volume, biomineral density. Again, no effect of the nursery. And the same for the rest, for the 7 skeletal traits. So again, we are keeping this wave attenuation, traits related to wave attenuation during this propagation phase. This is how it looks like the final PCA, the main drivers. I won't enter in detail, but then the take-home message that I would like you to take. Of course, growth and survival metrics are important. They are useful, and we should keep them, of course. But we have found that what is leading to this increased coral growth, in our case, we found that there was a higher metabolism, photosynthesis, respiration, and calcification rates. We think that this is potentially due to enhanced feeding on the nursery environment. And this was unveiled thanks to this multi-trait approach. In general, the nursery propagation didn't have an impact on the majority of the traits, which is a good sign. Also, we need to take this between brackets because this is our findings related to this species in a nursery propagation on the Northern Great Barrier Reef. And despite the time effort constraints, we still consider that this multi-trait approach can inform restoration to optimize their practices. As well, with this exercise, we identify traits that are more aligned to ecosystem services and processes. And the final message, nurseries are fantastic at growing biomass without any cost for certain ecosystem services. And with all, thank you very much for your attention.
We have time for a couple questions. In your trait measurements,